Hello again, and welcome back to part two of the Apollo Guidance Computer Block 74 project. Today we're going to be talking about the registers within the AGC. These are what's called part of the central processor within the computer. And I think it's a good way to kind of start understanding how the computer works and kind of breaking down some of the functionality, looking at the some of the simpler parts to start off with before we move into things that are a little bit more complex. And really, this is kind of the approach that we talked about last time, which is let's break things down into bite-sized pieces. So, got a quote here from Saint Francis of Assisi, whether he said it or not, but it's the old, there's only one way to eat an elephant, one bite at a time. So we're going to look at our computer one bite at a time. And so we're going to kind of focus on kind of the area in this kind of pink area here. This is an overall diagram of kind of sort of block diagram of the Apollo guidance computer. So as we go through a number of the key components, we've got a clock, and that's going to generate all of our timing pulses that we need to synchronize everything throughout the computer. We'll have a sequence generator that generates all of the micro pulses or microprogram pulses used to control the various aspects of the computer. And we'll get to that. That's fairly a complex piece of logic there. We've got memory timing. This is actually something that taking advantage of some more modern components. We're going to be using modern erasable, electronically programmable memory for the ROM portion, and we'll be using static RAM for the RAM portion. So because we don't have the core rope modules that Apollo used, some of the complexities around memory timing and amplifiers and senses, things that we just don't need to worry about. The modern technology will take care of that for us. But we'll still at least understand some of what the timing looks like as to how we kind of interface between how the computer is designed to operate and the technology that we're going to use to implement it. Kind of coming back up at the top here, we've got a variety of counters and interrupt priorities. This is something we'll probably look to go into more detail later, because that's basically where the spacecraft itself would be able to launch interrupts. Some of these are actually the keyboard. So the interface to the Apollo guidance computer was a module called the DISCI. You've probably seen it on videos like Apollo 13 or other, whenever they tend to show the Apollo missions, there's the little computer with the little keyboard and lights and the nouns and verbs on it. And that all kind of comes through this kind of priority interrupt. So every time someone presses a button on the key, it actually launches an interrupt that causes the computer to do something about it. We also have what are called the kind of addressable central registers. And I'll talk a little bit about what that means when they say that these are addressable. And there's the A, L, Q, and Z. We have the arithmetic unit, and this is the adder that does the computations and the various registers that go into that. And then later we'll talk about there's input and output channels to talk to various components of the spacecraft. There's what's called SQ, the instruction decoding. So this is kind of what connects the registers and the information that we store as the computer processes data to the sequence generator. So every time we load an instruction for the computer, it's going to generate a whole series of microprogram pulses that talk to other components across the central processor to either load registers or registers to put data onto the bus, or do a mathematical multiply, divide, add, for example. So really, we've got data that comes in on the right bus that goes to our instruction decoder, that goes to the micropulse, which then kind of goes everywhere to tell what registers to read data off the bus, what registers to write data onto the bus, if math functions need to be done. So these will start getting fairly complex. So we'll look at those a little bit later. There's also a couple of like the memory address register, and that's tied very closely with kind of accessing the fixed and erasable memory. We'll also get into a little bit of the memory bank registers. One of the challenges is that between the Block 1 and Block 2 Apollo guidance computer, of course, the demand started to increase. The computer was being asked to do more, and as they went from Block 1 to Block 2, they increased the size of the memory. Now, because of the sort of the address register size didn't go up, they had to start using some kind of fancy techniques around memory banks. So, you would use the memory register to kind of access contiguous sections of memory, and then you would have multiple banks in order to kind of switch to which bank of memory was being used. So, for example, we talked about how the Block 2 has 2048 16-bit words of erasable memory. The Block 1 only had 1024. So it was designed, a lot of the original logic and coding was designed around 1024 bytes of memory. So they had to kind of introduce these banks to be able to access the extra memory for both RAM and ROM as needed. So we'll get into that. That's, again, a little bit more complex. And then there's the local memory register. So this is the G register, which really is the kind of the middle ground between memory and all of the other registers. So basically, if you want to write data into memory, you would write it into the G register, and then that would push that into the appropriate. I mean, if you're writing, you would go into erasable memory. If you needed to read data from memory, it would come from memory, either fixed or erasable, to go into the G register, and then it would get used by whoever else needed. There's also some interesting not control, but logical operations that the G register can provide. It does some shift register left and right, depending on what's needed with the data that's coming back. And then there's parity. I mean, this is not something we need to be as concerned about with our kind of replicate that we're building. Parity is really a way of kind of checking the contents of memory, as it's read in and read back out, to make sure there are no memory errors. Now you can kind of understand in a older computer using more primitive memory technology like the core rote memory, a little bit more prone to bit flips, and then you kind of add the complexity of now putting it into space where you have cosmic ray events, solar storms that can also cause bit flips in memory. So you have parity, which will always kind of check to see, do we have an even number of bits in our particular word or an odd number of bits? Apollo guidance computer uses odd parity. So the idea is that if any bits get flipped in memory, you can at least detect that there has been an error, and kind of reread that memory in order to correct that particular error. And then there's like some special gating that we'll talk about a little bit later. So that kind of at a high level is the kind of the landscape that we're kind of playing within, and we're going to focus on kind of these to start. And actually, we'll even start more simply with just kind of the central registers that are in the CPU. So there's a couple key documents that we're going to be using for part of this. The first one, and this is the AGC Information Series, Volume 32, Block 2 Machine Instructions. And this is a very invaluable document that we'll probably use this more as we get into like the control pulse generation and sort of instruction logic, because this actually tells how each instruction is kind of implemented in a whole bunch of different control pulses, and when do we load registers, when do we write to registers, and then there's kind of the holy grail, if you will, the ND 102.1042, the LEM or LEM guidance navigation and control systems manual. I'll just quickly flip those up so we can take a look at those. But so we have this one, which is like a very, very in-depth document. You can see it's scanned in the original scan. Probably it's seen some better days, but it's basically details like all sub instructions. It details registers. It details order codes. Like this is basically very, very in-depth detailed description. You've got schematics and circuit diagrams of the guidance computer. So again, this is going to be instrumental in kind of the description of how everything is designed to operate. And then we also have this Block II machine instruction document. From this case, it's 1965, so there have been some updates, and we'll kind of, as we go through, we've actually identified a couple of little errata here and there as you go through. But this has, again, all the instructions, how they're set up, and some of the things that are most valuable that we're going to be using. I'll just kind of scroll down into that document. These are those control pulse diagrams that I was mentioning. So for example, we've got this, sub-instruction TS0, and it gives you basically what the kind of the op code is for that particular instruction. Some instructions are more complex. So if we look at things like multiply and divide, there are multiple steps to that particular instruction. So what step you're on. And then each instruction, there's a variety of kind of time slices as the kind of computer goes through each, what they call action code. And so kind of T0, we implement these control pulses, and then times it 2, these control pulses, and so on and so forth. And there's a couple that we get into more conditional logic, which we'll talk about later. For example, in time pulse 4, you can see here, we've got 1 if BR, CBR. So in order to do conditional branching, the AGC implements basically two registers, so BR0 and BR1. So basically 2 bits of data to basically give you a branch code. And then depending on the contents of that branch code, we can say, okay, if it's 0, then we basically, in this case, we would do an RZ and then a WY12. And we'll go through these in more detail as we look at each register. If that branch register is equal to 1, then we do an RZ, a WY12, and a CI. So it's like a clear, or that's set carry bit. We've got 3 if it's equal to 2. Then we've got RZ, Y12, and CI as well. And then you've also got little things here like if A16 or 15 is equal to 2, it basically gives you a few little kind of branches that you may need to kind of take into account as you implement. But for the most part, we'll be focusing, at least right now, on this particular document because it gives really good descriptions of each and every one of the registers. Okay, so back to the story. I'm just going to minimize myself up here in the corner. So this is a more detailed breakdown of the various registers, or what's called the central processor functional diagram for the AGC. And this describes, here we talk about some of these central registers. So these are all the different registers. You've got the accumulator here, the A register, the low order product, the L register, Q, this is called the quick register, the program counter, the Z register. We've got the arithmetic unit, which is made up of the X and the Y register. And then we have the buffer register, or B register. And these are sort of the main kind of more general purpose registers. You'll find in the Apollo guidance computer, because they were trying to optimize how the computer performed. Each register sometimes has its own little quirks and little extra features that they've added to either simplify certain mathematical operations like division. So none of them are, I guess, would be truly just kind of generic registers. They all have some additional functionality that needs to be implemented along the way. We talked about kind of that G register, that memory buffer register, and this is what kind of handles data going from memory and out. And this kind of is when we say out, we have our kind of write bus or our data bus within the AGC. This is where we think when they talk about things like write amplifiers, because again, we're not going to be implementing it using some of the more primitive technology that was used during the construction of the Apollo guidance computer. We don't really have to worry about some of these write amplifiers and sense and things like that when it comes to running the bus and data onto the bus. Each register, you'll notice, has kind of what they call a service. So there's for the accumulator, there's the A service. both on the input side and then on the output side. And this is just to implement certain logic around, for example, when do we write data into the accumulator? Here they've got a little WA signal, which is a write A. So that means, when do we want to input data into the accumulator? Well, it's, there's going to be a signal pulse that's a WA signal pulse. And there's a few other conditions. We'll kind of see those as we go through for each register. And then, of course, you've got the register itself. And then you've got the read service, which is when do we read data out of that register and put it onto the bus. So here there's a RA, which is a read a command, which would basically push that data out onto the bus. And then there's a few other little, oddities that we'll go through later that can push data onto the bus for a variety of other reasons. A few other registers that we'll just kind of briefly talk about here. Here we have the S register, S register, which is the memory address register, and then the service that's associated with writing data into that register. And then associated with that are, I talked about those different banks. So in order to access memory, they have a erasable bank service. They've got a fixed bank service, and then a fixed extended bank service, because they continue to add more and more fixed memory to store larger programs as they progressed. But all of this stuff, for example, all this kind of memory, this is all for driving memory addresses and how do we access the right memory. We'll all look at that later. The focus right now is going to be more on these kind of central registers and how they work. Okay, so we talked a little bit about what the central process registers are. So again, there's the Q register, the Z register, the B register, the X and the Y register, which are the operands for the arithmetic logic unit. There's the A and L register, which is the accumulator and low order product. So sometimes some of the calculations that were required by the computer needed to be what are called double precision. So rather than basically they'd use two registers to store the outputs for higher precision for some of those calculations. And then we also have what these called kind of like pseudo registers. So there's the C register, which is really just the ones complement of the B register. And then there's what they call kind of the U register, which is basically U stands for the U in sum, which is basically the output of the ALU. So as you put data into X and Y, and then depending on the mode, it'll do an AND, or it'll do it's adding and calculations, and that kind of output is kind of what's called the U register, if you will. And then that's kind of fed to different parts of the central processor. A couple of these are kind of, I've highlighted in bold, and these are registers that are also called direct addressable registers. So I'll talk a little bit about what makes these registers different. So for example, if I want to write data to the B register or the X or Y register, basically the main way to do that is those command pulses that I talked about, so that there'd be a WB, which would write data into the B register, or WY, which would write data into the Y register. Now, these exist for these kind of registers in bold as well. So there's a WQ and a WZ, for example. But we can also, these registers are also mapped to an address in memory. So if I were to write data into memory at a specific address, it would also go into this register. So there's you can, when you access and write the machine code and assembler for the AGC, there's a couple different ways to access and write data or read data out of these particular registers. So what we're going to focus on to start with is these, A, L, Q, and Z registers. They are part of the more simpler ones, and of course we'll start with the easiest first, which is actually the Z register, and then we'll kind of go through them as they get kind of increased complexity as we go through. But that will be kind of that, eating our elephant one bite at a time. Then we'll kind of talk about more the ALU, or the arithmetic component. So we've got the A service, which, as we talked about, was the accumulator, or sort of the A and the low order product registers. We've got the X and Y registers that are the operands, or the inputs into our ALU. And there's certain kind of, as part of the memory addressing mechanism, we need sometimes some of the information that comes out of the memory, or sorry, out of the summer, the arithmetic logic unit, to determine what memory addresses we want to access. So that'll be something we'll talk a little bit later as we get into these registers. In addition to those kind of central registers we talked about, there's the 12-bit S register, which is the memory address. May recognize that, well, 12 bits isn't enough to address all the memory that's in the AGC. So that's why we have these additional fixed bank register, erasable bank register, and fixed bank extended register, as well as the G register that we talked about. That's more of the brings data in and out of memory. So these are all related to memory, how we access memory, how do we address it, and how do we bring data in and out of memory. And these are kind of how that maps to the different components in this diagram here. And then we also talked about the G, which is more for data in and out of the memory. A few other registers. There's the SQ register. So this is the sequence register, basically the current instruction that we are running. There's the ST register. I mentioned that there's a 3-bit step register. So we can have potentially up to 8 steps per sub-instruction that we may need to go through. There's also a number of input registers and output registers, and these are more tied to I/O. And then throughout the system, there's several different little single-bit registers or flip-flops that kind of store data, whether it's carry out or carry in. If we need to store extra bits, there's the branch register that I talked about, the 2 bits for storing branch information, and a few others that we'll kind of identify as we go through each and every one. Maybe just to kind of digress a little bit, and this may more be a stretch goal in the future once we get the Block II up and running, is there were some notes that were taken in the it was kind of late 70s, or basically some conversations that were had with one of the original AGC designers and programmers, Hubler-Smith. And he kind of captured a whole bunch of ideas as to, if we were to do it all over again, or if the Apollo program had continued, what could a Block III Apollo guidance computer look like? And a lot of the kind of thinking around that is, maybe we simplify the kind of the memory layout. So instead of having all these blocks and having to do switching blocks of memory in and out, have more of a flat memory architecture, so that we can have larger register sizes and memory address sizes, so we don't have to do some of this back and forth with these banks. There's also talking about adoption of a Harvard architecture. I'll talk a little bit about that just in a second. The AGC is kind of more the traditional von Neumann architecture, and I'll discuss what the difference between those two is. But this kind of Harvard architecture would allow us to split out the erasable memory from the fixed memory, instead of addressing it kind of as one big kind of continuous memory map. Some of it is writable, some of it not. You basically treat it as 2 separate kind of pieces of memory, which in some ways kind of makes sense because the sizes of the memory are actually quite a bit different, right? So we've got 2048 of erasable memory, and then 36,000 words of ROM memory. So if you start addressing that memory directly, the number of bits that you need for an address register is going to be different for fixed versus erasable. And then because you have larger kind of memory addresses, you probably want to have an extended instruction word size so that you can store some more of those memory bits in your instruction. A few additional instructions I would have liked to have added to make things easier to program. Two's complement for negative numbers. So Ben Eater has a really good video where he talks about the difference between one's complement and two's complement. And that's really about how do you represent negative numbers in binary. So, binary, if you basically are just like 10, 10, 10, for creating, basically storing numbers, is how do you determine whether that number is a positive number or a negative number. And that's, the one's complement and two's complement are kind of two ways of kind of representing negative numbers using binary. One's complement is simpler, and that's really just the inverse of the number itself. So basically you take the bits that make up a particular number and you invert them, and that becomes the one's complement, or the negative version of that number. The only challenge there is that it results in a weird scenario where you have +1 and +0 and -0, right? So you can have all bits where all your bits are 0. So if you have 16-bit number, that's all the bits are 0. Well, that represents the number 0. Well, if you flip that and invert all of them, you have 16 ones, so 16 bits all full of the number 1, which then represents -0, right? So that really doesn't make logical sense, which is why in two's complement, they kind of address that by getting rid of the whole concept of positive and -0, but it makes some other elements of computations a little bit more complex. Then they had some concept of things like native mode, where they can run the computer in different modes, and introduction of a little bit more additional registers around interrupt vectors, so making the interrupt mechanism a bit more flexible, things like return addresses for subroutines, and then what they called, core sets, that they could run sort of subsets of different bits of programming, and do that a little bit more flexibly. Like I said, I may talk a little bit about just the difference between Harvard architecture and von Neumann, but we won't talk too much more about the Block 3 until we get further down the project. And once we've solved for the Block 2, then we can look at making the Block 3 happen. And one of the things that why I'm kind of designing the computer and the way that those kind of circuit boards that I showed on the last session is making it very much modular, so I can like plug cards in and out. So if we decide to start expanding or adding new functionality or features, we can kind of pull out one of the the old sort of S register, which is the 12-bit memory address, or sorry, the memory address register in the current Block 2, and we could put in a new one that has additional bits for larger memory access. Like I said, before we wrap up today, I'll just kind of talk about the difference between Harvard architecture versus von Neumann. So most computers that we typically, like our desktop computers, I mean, this is 100%, but generally follow a more of a von Neumann architecture. And this is where you've got your control unit, sort of within your CPU. You've got your ALU, which does your math, IO, which is input and output, and then you have your both RAM and ROM, which is kind of looked at as kind of a continuous segment of memory. Some of it you can write to, some of it you can't, whether it's erasable or fixed. But basically, you kind of treat memory as kind of one kind of continuous field of memory. In Harvard architecture, you actually you break out and put on separate buses, memory that comes from your kind of fixed memory, as well versus memory that's erasable. So you could actually have, two memory addresses that are exactly the same, but one that's referring to, for example, memory address 1000, it could be memory address 1000 fixed, or it could be memory address 1000 erasable, depending on what bus and what memory was located in. Whereas with von Neumann, you only have one memory address 1000, and depending on what your memory map is laid out to, it is, it could be fixed, it could be erasable, but you don't have to determine which 1000 that you're referring to. So that was one big difference. And again, this was, for the Block 3, the intent was there's a lot more fixed memory than there is erasable memory. So this would kind of simplify some of the instructions on managing that disparity in memory sizes. Anyway, I think that's probably good enough for today. Again, if you're interested in seeing what we do next, please subscribe and send me feedback, send me questions. More than happy to answer as we progress. And then in the next video, I'm going to actually go into one of the first architectures. We're going to start talking about, or first registers. We're going to start talking about the Z register. We'll see you next time.